Let's try to understand position velocity graph and then get ready for derivative of derivatives or higher order derivatives, in which first application will be to consider displacement, velocity and acceleration, and figure out when the object is slowing down or speeding up or approaching or going away, and so many different kinds of problems, right? So let's first try to understand the basic graph and find our way through the whole exercise. So the question here is, graph below represents position s of t in meters and velocity v of t in meters per second for an object. Write equation for the position function. Assume maximum displacement of 16 meters. Find velocity function from your equation. Find velocity at t equals to 3 seconds. What does the negative velocity represent in the graph, right? So these are simple questions which we'll try to understand with the help of this figure. And I hope it gives you more or less the concept of the relation between position velocity and acceleration. Now, I'm taking these simple examples again and again. Now, my idea of taking this simple example again and again is to get the point clear that position, velocity and acceleration is a very important topic, and we need to really understand it before getting into derivatives and higher order derivatives, right? So I'm trying to prepare you for that. So here is a graph. This graph solid line is displacement, and this dotted line is actually representing velocity of the same displacement. You believe it or not, it is the same object and the same displacement, which is being represented by two different graphs. Of course, the units will be different, right? So we'll consider units also. Now, the question is, write equation for a position function. Assume maximum displacement of 16 meters. So getting back to our functions, this is 16 and that's the vertex, right? And another thing what we find here is the intercepts, the t-intercepts, which are at 0 and 4. The shape of the graph is parabola inverted. So it gives us an idea that displacement s of t should be of the form a times t minus 0, the first intercept, times t minus 4, right? So that should be the equation for this. And now since we know this point, and that is at 2 we have 16, right? So we'll find what a is. So it is 16 equals to a times 2 times, with 2 minus 4 is minus 2. And from here we get a equals to minus 4. And since a is minus 4, we get s of t equals to minus 4t times t minus 4. So that is our equation, and let's number it. So this is equation number 1 for us. So we have found the equation for displacement, right? Now what? Find velocity function from your equation. Now, equation and velocity function. Velocity is derivative of displacement. So it's a good idea to write this equation in expanded form. So it is like minus 4t square and plus 16, right? So that is the way. Now what we will do is we'll find velocity, and velocity is what? Velocity is the derivative of s of t. So the derivative of, let's say, s dash t, right, is equals to minus times 4 times 2 is minus 8t. So that gives us velocity of this function, right? Now I think we made a mistake when we have to open this. 4 times, it should have been t here, which I missed, and I was thinking what's wrong. Now that's fine. So it is plus 16 also here. Now that's right. Now this line really represents what my velocity is. Good job. Now see, if you now consider this line, you say 16 is your y-intercept. Okay, that's fine. So it is indeed same as this, but the units are meters now per second. So the units for displacement when we're talking about is meters, and when we're talking about velocity, it is rate of change of meters. So it is meters per second, right, for velocity. Perfect. So as you can see now, if this graph's equation is minus 4t times t minus 4, which reduces to minus 4t square plus 16t, then velocity, which is the derivative of displacement, is minus 8t plus 16. So 16 is my y-intercept, and as I move 1 unit, I move 8 down, and second unit, I move 8 more down, 16 down, and I get to 0 value. So perfect. So indeed it represents velocity, correct? Now the next part is find velocity at t equals to 3. So we can read from the graph, but we can find from here also. So when we say find velocity at t equals 3, we really mean we'll plug in 3 here for t and calculate. So we have minus 8 times 3 plus 16, right? Which is 24 minus plus 16, right? And that gives us minus 8. And the units are meters per second, right? So let me write here time in seconds. I'm not writing y value is meters or meters per second, but you can now make out when we're talking about displacement it is meters, and talking about velocity is meters per second. So we answered third part. What does the negative velocity represent in the graph? Now that's a open kind of a question. Negative velocity means what? Negative velocity means negative slope on displacement. So I will say when the velocity is negative, then the object is going in the negative direction. So if I'm saying that going away in this case was positive, then coming towards is negative. So that could be one explanation, right? So now we could have different explanations for part, I should say D, which says what does the negative velocity represents here. So if we are talking about positive velocity is going towards north, then negative velocity means what? It's the reversing of direction, right? So first let's understand what is zero velocity. So when the velocity is change, right, so before that it is positive velocity. So negative means reversal of direction. So I should say reversal of direction, right? So that is what the negative velocity is. So what we normally say is positive means going towards north or east or right, right? So negative means when your position is changing towards south or towards left or decreasing, right? So those are the different three terms which we'll use alternately, right? So it could mean either of those terms, but in any case it means reversal of direction. Now that gets me back to what is zero velocity means, right? So zero velocity here will means the object is momentarily stationary. So zero velocity, let me add this here also. I didn't ask this question here, but anyway, when we say v of t equals to 0, that means stationary or stop, right? Not moving. And of course the time is moving so fast, so it is just for moments, right? So momentarily stopped or momentarily stationary. So that is how we have to see velocity, correct? So I hope this gives you a good idea about how velocity and displacement is concerned. Now you know what is acceleration. Acceleration is derivative of velocity. So as an exercise, you figure out what acceleration should be in this particular case and plot it on the same graph, of course with different units, meters per second square. And then let's move on to similar questions before really getting into interesting questions about higher order derivatives. I hope you are enjoying this learning process, and soon you'll be masters in solving problems on position, velocity and acceleration. Thank you and all the best.